Hello, wait, no. Hello. I can't look at you, I need to look at you. Hi, my name is Janae, and I'm going to be going over the concept review of liquids and solids, and a lot of the information will be found from the Cengage Learning book, AP edition. So let's jump right in. But before we go, if you are another AP student who's not learning from this book, you can look in the description box below, because I will list all the sections that the video is going to cover, as well as the timestamps, so you guys can go ahead. So if you don't want to watch the whole video, you can go to that specific timestamp. Okay, let's go. All right. So there are three main types of intramolecular bonding, but we're going to go over the two main types, and then we're going to go over the third one in a minute. Two types, right? Ionic and covalent. Now, ionic has a metal and a non-metal, and right here as an example is table salts. Table salts is formed of NaCl, which is its chemical formula, so sodium being the metal and chlorine being the non-metal, which combines to form crystals. Ionic bonds always form crystals. So another example that is used, lithium chloride, which I will put a picture up of now, is used as a brazing flux for automotive parts for aluminum. Now, what's a flux? A flux is a chemical compound which is applied to the metal that is wanting to be brazed, so that it will add more oxygen, as well as creates a better combination between the metals that will be being brazed together. Now, covalent bonds. There's two types of covalent bonds. Non-metals, two or more non-metals put together, and metalloid and a metal. So a classic example, which is used all over the place, is water. So water's chemical compound is H2O. H2, so two of hydrogen being combined together by oxygen, is your water compound, this is what it would look like. Water, obviously, all non-metals. Now, if you were to take another example of a covalent compound, is boric acid, and I will put a picture of it up now. Boric acid can be used as an antibacterial and is also found in most acne treatments, and is used to clarify skin or help fully cleanse any injuries. Now, that third one that we were going to come back to is metallic bonds. Now, metallic bonds are the sharing and combining of metals. So, for example, like copper and tin to create like wires for electrical systems, or in other terms like metal alloys. So it's literally in the name, super easy to remember. Metal plus metal, and commonly the name of a metal plus a metal will be known to be an alloy. So some other examples, like bronze is made out of copper and tin, and brass is made out of copper and zinc. Alright, intermolecular bonds. Inter, meaning they correlate in between the two molecules. So let's go back to our little models in front of us. So let's just say these are both molecules. So the first force that I'm going to explain to you in a minute, I'm going to show on the models first and then explain. So trying to connect between intermolecular forces, it would look like this. Now let me explain. The force that I just showed you is called dipole-dipole. So dipole-dipole forces attract the opposite end and line them up so that they will attract. As you can see here, the blue lines are connecting the positive and the negative side of the molecule. Now you're wondering, how can a molecule have a positive and negative side? A positive and negative side. When bonds are formed and when you share or gain or lose electrons, you are creating a type of attraction for that molecule. So let's just take hydrogen fluoride. It's very commonly used. So let's start putting it in our diagrams. So let's just pull one of these out off to the side. Let's draw it bigger. So we're just gonna zoom in on this. So now, if you just had to imagine, we're just gonna draw an imaginary dotted line right down the middle. So this is our hydrogen fluoride model, right? Hydrogen fluoride. Now, hydrogen fluoride. You put the two together, right? So it should look something like this, which is what we have right here. So just remember, this diagram is showing it like this. This is what it looks like. Hydrogen fluoride. Since we gained an electron from hydrogen. This will be hydrogen and this will be fluorine. Your hydrogen will become slightly negative and your fluorine will become slightly positive. So this is where we get our two sides of the molecule and how they are positive and negative. So it basically comes from how the bond that we were talking about in intramolecular forces, how that acts up and plays out to form the two sides polarity. That's dipple-dipple. And a lot of people like to mistake these two different bonds, which I'm going to talk about right now. There's two different bonds that people get confused on: hydrogen bonds and dipple-dipple bond. Dipple-dipple is a very well commonly known bond, and hydrogen bonds people think is just a completely separate type of bond. It's not. Hydrogen bonds, this is why I put a 1.5, are a type of dipple-dipple bond, but they are very, very strong because is that hydrogen can only bond in a dipple-dipple force through fluorine, oxygen, and nitrogen, or otherwise known as FON. Hydrogen bonding with one of these will have a very, very strong electronegativity difference, and I will talk about electronegativity in a minute. The second type of bonding in intermolecular forces is London dispersion. London dispersion occurs in every single molecule, no matter if it's water, salt, anything. It will always occur and will help pull all the molecules together. The only time that London dispersion will not be a short-term force is for the one and only, and if you can't tell, this is a little crown, and I like to call these the noble gases. Nobility, crown, get it? Now it's just a gas, now it's a no, okay. Noble gas. Noble gases are only held together by London dispersion. It's the only force that is holding them together that is an intermolecular force. The last type of intermolecular force that we'll talk about is ion-induced dipole. So it was really hard to try and model how this would look in actual 3D, so I'm going to show you on the board. Ion-induced dipole's definition is that it is the attraction of an ion to a non-polar molecule. So here I have shown that this non-polar molecule is water, and this ion is just a Cl ion. So if we look here, these are deltas, and that means slightly positive or slightly negative. So since I have a little minus, that means it's slightly negative. So this ion will travel towards this molecule because it's slightly negative, and this molecule is slightly positive, and that's what ion-induced dipole is. Electronegativity, I just want to quickly go over this because I know maybe you didn't learn it yet, or you have learned it and you just need a recap. So electronegativity measures the tendency of an atom or a molecule to attract a bonding pair or an electron. So this is just a chart to understand each element has its own electronegativity. Electronegativity, and this is just the chart and the difference. So if you were to subtract like hydrogen and fluorine to get a certain number, you would go by this scale to understand what type of bond it is. So if the number is above 1.7, it's an ionic bond. If the number is between 1.7 and 0.35, it is a polar covalent. And if the number is less than 0.35, it is a non-polar covalent bond. Two other properties we're going to be looking at in the liquid state section is capillary action and viscosity, but today, for right now, we're just looking at capillary action. So there's two things in capillary action that people confuse a lot, but we're going to explain and identify which one is which. So cohesion and adhesion. The dictionary definition of adhesion is the forces in which the liquid molecules interact with the container. And as if we look on the board, this substance in the graduated cylinder, there's water, and you can see that the water molecules are slightly negative, and the actual graduated cylinder is slightly positive, which causes it to form a concave line. So when people say, or when instructions say on your lab report, read from the bottom of the meniscus, that means read actually at the bottom point under that line, because that's what's going to show you how much liquid there actually is due to adhesive forces causing the water to go up, giving incorrect measurements. Cohesion is forces which interact with the liquid molecules within themselves. So this is a nonpolar substance. A good example to help explain cohesion, like on a test or something, is mercury. As you can see, as we zoomed in here, it forms a convex shape on the top because these are slightly positive, as well as the graduated cylinder being slightly positive or convex on top. Another type of property that is used to understand a liquid is the viscosity. Now, viscosity means the resistance to flow. So, for example, like I have a little shot glass of water. Water has a very, very low viscosity. Pours right in. There's nothing stopping it, nothing prohibiting it from flowing down super, super slow. Now, if we take a simple syrup has sugar and water combined. Its viscosity, as you can see, is not like water, but it is not super thick either. So when it flows, there's a little dip in it. It doesn't flow as easily as the water did. If you take something like corn syrup, which is super thick, you can even see just coming out of the bottle, extremely hard to flow. The viscosity is so high because all of these molecules are staying together and forming such a thick liquid that when it pours out in slow motion. That's so cool. So that's viscosity. Before moving on to the next section, we're going to talk about the structural models for liquids. Now, when scientists were discovering and figuring out structural models for solid, liquid, and gas, for solid and liquid it was very, very easy. For these reasons being that gas particles were so small and they were traveling so fast and they were so far apart from each other, which made it easy to have a simple model. Now, solids on the other side, solids had strong intermolecular forces, but very minimal movement, so it was really easy to make a tight, packed together model. So both of them had simple models, but here's the problem with liquids. Liquids have both strong intermolecular forces as well as rapid, well, not rapid, but significant or high molecular movement. So for that reason, it was really hard to make simple models for liquids. But through a lot of research and study and advances, there has been a study come out called spectroscopy, which was invented and founded by Joseph von Fraunhofer. So the founding fathers, or the main inventors, you would say, of spectroscopy were Isaac Newton and Joseph von Fraunhofer. Now, Isaac Newton, the reason he's so important is this, because not only did he discover and realize the forces of gravity, but he also discovered the way that light affects certain things. So the whole spectrum, color spectrum, was founded by him. But von Fraunhofer actually took the research that Isaac Newton did and created spectroscopy, and the definition is going to be on the screen now. Spectroscopy is the study of manner in which substances interact with electromagnetic radiation, and due to this make it possible to follow the rapid changes that occur in liquids, and therefore having those changes in occurring in liquids as they can see them through spectroscopy, they can understand and make structural models for liquids. Okay, so moving on to section 3, we're going to be talking about the structures and types of solids, and the way we classify solids is into two groups. So we have crystalline solids and amorphous solids. So crystalline solids, basically the components are arranged in a certain order, so the key word to remember for that is order. But amorphous solids are scattered components. They are just all over the place, and the ions and everything are just clumped together, and the keyword to remember for that is disorder. Now, looking back at the crystalline structure, or the crystalline solids, they are represented by what is known to be a lattice. So a lattice is a 3D structure that would show where atoms, ions, or molecules will be placed, and the guy who actually discovered this was Augusto Bravais. He's a German scientist who figured out the unit cell, which is a small block within the whole lattice, if that makes sense. So here we have what a unit cell would look like, and this is what a lattice cell would look like. Here we have what a unit cell would look like and what a lattice would look like. So a unit cell is a small piece of a lattice. So basically, to show, to understand this, I have these 3 little blocks. So these are like giant Lego paperclip holders that I had lying around. So an easy way to understand, oh, you cannot see me. Okay. An easy way to understand this through a model is that this would be a unit cell, but when we put all 3 of them together, it would be a lattice. So again, unit cell, lattice. So in the first subsection of the third section that we're going over is X-ray analysis of the solids. Now, 2 men were very important in figuring out X-ray diffraction, and those 2 men were Max von Laue and William Henry Bragg. William Henry Bragg and Max von Laue created 2 new sciences while in college, which were the X-ray analyzation of crystals. So he created X-ray crystallography, and William Henry Bragg created X-ray spectroscopy. William Henry Bragg founded X-ray spectroscopy, and those 2 sciences together form X-ray diffraction. The definition of diffraction will pop up on the screen now, saying diffraction occurs when beams of light are scattered from a regular array of points in which spacings between the components are comparable with the wavelength of the light. So this whole system is used to determine interatomic spacings. So the definition of interatomic, or just atomic spacings, will come on the screen now, which means it refers to the distance between the nuclei of atoms in a material. So the second subsection that we're going to go over is the types of crystalline solids. So there's 3: ionic, molecular, and atomic. So the ionic have so the key thing to remember for ionic crystalline solids is that they have ions at the endpoints of the lattice, which shows the type of solid it is. So for an example, which forms crystals, it would be sodium chloride, so NaCl. Molecular crystalline solids have covalent bonded molecules which are discrete at the end of each lattice point, and that is the thing to remember for molecular. So an example would be sucrose, which is table sugar. And the last one is atomic. So atomic have certain types of atoms at the end of each of their lattice points. So the 3 main elements which are included are carbon, boron, and silicon, as well as all metals. So an example of this would be a diamond. So it'd have carbon at each of the ends of the lattice points. So in section 4, we're going to be talking about the 2 types of alloys that there are. So this is the subsection. So there's substitutional alloys and there's interstitial alloys. So substitutional alloys are, the best way to remember this is that the similar atom size. So some of the host metal is replaced by a similar sized atom metal. So for example, brass is made up of zinc and copper, and since there's somewhere along the same area of the periodic table, you can see here in the little example, the zinc atoms and the copper atoms are in similar size, so they are able to form a substitutional alloy, whereas an interstitial alloy is formed when some of the gaps are filled by smaller sized atoms. So smaller sized atoms, metal or non-metal. So for example, carbon steel is made up of iron and carbon. You can see that the smaller sized atoms of the carbon and the filling holes which are left over or left open by the ion. So the subsection 2 that we're going to be talking about is network solids. So a network solid, which the definition will pop up on the screen now, is a substance containing strong directional covalent bonds to form a solid that might be best viewed as a giant molecule. So these are known to be giant molecules. So the known properties of a network solid are typically, not always, brittle and not a good conductor. Now, brittle, obviously, we know that diamonds are a network solid. Brittle is not the word used to describe a diamond. Why is it so strong and why is it not brittle like network solids are typically supposed to be is because the way that the carbon is forming a tetrahedral structure when they are bonding together. Now, graphite, on the other hand, is a perfect example of a network solid being brittle because each of the layers are strong horizontally, but when vertically looking at the connections or the bonds, they're super, super weak and can snap easily. So the third and last subsection of section 4 is semiconductors, and there's two types of semiconductors, N-type and P-type. So N-type is increasing electricity. Sorry. N-type increases conductivity by adding more atoms with, and this is the key word to remember, more valence electron atoms, meaning they should have more electrons in them. So that's N-type. So P-type is named due to the positive holes that are left in by certain atoms, and they are used and kind of identified as carriers. So when you add an N-type and a P-type semiconductor together, you get an NP junction. And this will create a region in a certain metal, non-metal, or substance, which will create the N-type or the N-type region to have a positive charge and the P-type region to have a negative charge. So I just moved the board over so you guys don't have the glare of the light on the board because I noticed that in the last video or last section. So the next section we're going to be talking about is the change of state and vapor pressure. So we're going to talk about vapor pressure now and vaporization. So the definition of vaporization will be put on the screen now. Vaporization is the clear evidence that molecules of a liquid can escape liquid surface through a form of gas, and vaporization is known to be endothermic. So the actual definition and the way that scientists can calculate how much of a substance has vaporized is by using the heat of vaporization, or delta H vap. And basically it's saying that the energy required to vaporize 1 mole of a liquid takes 1 atm, and this is what is known as heat of vaporization, or the enthalpy of vaporization, and that's its symbol. The symbol is, the triangle means it's a delta, so it's the change of heat of vaporization, so that's what the VAP stands for. Right. So when we continue, there's one more property that we need to go over in vapor pressure, and that is condensation. So condensation is the opposite of evaporation, but it is super important to help equalize the number of moles in the actual container. So condensation, by definition, is the process in which vapor molecules reform into a liquid. So condensation occurs when a liquid is in a closed container and is forming back in... Oh. Condensation occurs in... Oh my goodness. Okay. Condensation occurs when a liquid has been placed into a container, heated up, and then the gas particles form, which is evaporation. So basically it's the opposite. So when the container is closed, it's reforming back into a liquid. So that is condensation. So eventually in a system, when the condensation rate and the evaporation rate are equal, the system is at equilibrium.
So the chart that you're seeing right now is the change of state chart, and it is temperature versus time, and the constant rate is what is the time. As you can see, going from ice to steam, it's gradually showing the transition phases from ice to water and water to steam. And this is what would be referencing, or otherwise known as a visual, for the delta H of fusion, or the enthalpy of fusion.
Okay. Hello. I can't look here. Okay. Chemistry. It is a very complex, confusing subject, but I'm here to break it down for you. And today's topic that we're going to be going over today is liquids and solids. Science. It's complex, confusing, and one of the most